Welcome, everybody. This is the second class for sustainability and resilience at Northeastern. Thank you all for coming back. Thank you all, everybody online, joining us. If any problems with sound or video, please send something in the chat, and we can try to respond to that as we go through. We're very pleased to have Michael Kane, professor from Civil and Environmental Engineering, is that correct? Yep. And Joe Lalley, Associate Vice President for Operations and Facilities, talk about energy challenges that are facing here at the university and in general. But before we get into that, we thought as a way for this course class to go forward is to have some selected students who are registered for this class to do a little bit of research on some other ideas or things going on or in other campuses related to this topic, and just kind of come up here and just do a quick look for everybody here, for everybody online, kind of to kick things off. And then we'll turn it over to Michael and Joe, and we'll have some questions, maybe do some breakout rooms, and at the end of the class, we can kind of get into some logistics for the registered students to go through. Any quick questions, thoughts on what we have spent so far? Great, so without further ado, I'm going to invite Yvonne and John just to do a quick run through of their what they see over here at Brown. Do you guys want to come up here? Just spend a couple minutes and run through it. If you can, come over here because the video screen is right there, and just do back and forth on me. Thank you, guys.
Yeah, sure. So we look into Brown University's net zero goal or path to net zero. They know that greenhouse gases is one of the biggest threats. So reducing those emissions, reducing their emissions, and reaching a net zero goal. In order to, their goal is to reach said goal by 2040. And within 4 years, they plan to reach 75% of that goal in the next 4 years. And also, they plan to invest over $2 million in order to achieve their goal. Part of the over $2 million in investment will be in equipment, including LED lighting. They will also have entered into purchasing power agreements with solar and wind farms, and in Texas, and currently one that's being developed in Rhode Island. That's over 240 acres in a currently gravel site. They're also using automated systems in order to monitor so that they have a live feed of what exactly the amount of energy that they're using, and finding ways to reserve or conserve energy.
So just this process is happening over the course of 4 phases. So the first phase is in 2020, and Brown started to purchase the renewable energy from wind and solar sources. Phase 2 is in 2022, Brown is converting their heating plant to a post-consumer bio oil as their primary fuel, and they're using natural gas as a backup. And this is going to happen to roughly 100 buildings that are affected by the central heating system. And they're going to convert it to low temperature hot water that's heated by the renewable energy. Phase 3 is going to happen over the course of this year through 2038. And they're just going to be upgrading the central heating loop. And then phase 4 happens in 2038, where they convert the heating plant to fully renewable energy using the bio oils as a backup. And that is pretty much their general timeline. So thank you guys.
Great, thank you very much. Next we have Iman, Keenan, and Caitlin.
All right, so we found an article on Wesleyan University and their processes to try to improve their energy management towards sustainability. So the university found that about 75% of their emissions are related to energy usage. So to combat this, they made a conservation policy in 2014, which entails setting set rates for temperatures in buildings across campus. They use smart thermostats to do this. And in addition, they encourage students and faculty to close windows and turn off electronic devices when they're not used.
So this article that Wesleyan put out kind of framed their efforts in like a 3-stage process. So the first one was their resources, and then, energy conservation. The second one was their energy efficiency, and then finally they talked about their energy procurement. And so the second category, energy efficiency, basically had to do with like basic building envelope improvements, so storm doors and windows. And then they have photo and infrared sensors in many of the classrooms and dorm buildings to sense occupancy, to scale back on lighting and lab equipment use when buildings aren't used. They have water meters spread out through campus to actively measure the building's state of necessity throughout the day out of the building level. And then some general improvements in their HVAC. They switched from oil use in their heating and cooling to natural gas. Something that I thought was particularly noteworthy was in their layout for proposed developments and modifications, is that for every new replacement of a high energy use system, so like a big piece of equipment, they have to perform a life cycle cost assessment, I should say LCCA, which would look at least 20 years down the line into the greenhouse gas impacts, the cost, and the maintenance schedules and requirements and they have to perform this before implementing any upgrades in equipment. And then another notable thing is that all new buildings constructed on campus need to meet at least a LEED gold certification before they can be constructed. And the last sort of tranche that they outlined was their sourcing of that.
Yeah, so they were looking to solve the problem of where they could source their renewable sources. So their first step was to create this utilities carbon neutrality master plan, which was essentially a map to reduce energy usage and provide power needs on campus from within the campus. So some of the ways they did that were through they developed solar photovoltaic systems, and these added renewable energy to the New England grid, and it helped to prepare Wesleyan for long-term carbon neutrality. Then they used natural gas cogeneration systems, which is the simultaneous production of 2 or more forms of energy. And this was added to 2 campus locations, and it formed the first microgrid in Connecticut. And then, so they started purchasing B20 biofuel. So B20 biofuel is a mixture of 80% number 2 oil and 20% cooking oil. So this replaced all of Wesleyan's oil purchases, and it reduced greenhouse gases by 200 tons annually. And then they are a member of Solarize U, which is a Connecticut state-run solar discount program. And it included the installation of solar panels on like employees or just sort of members of this union. And so what that did was it was added to alumni homes and such, so that Wesleyan community members would lower their monthly electric bill and their footprint. And lastly, they had the Solar Rover launch, which was a student-made mobile power source, and it was launched in fall 2020 to use in on-campus events.
And while Wesleyan might not be at the very forefront or the vanguard of the transition to renewable energies on campuses across the US, something that kind of drew us to them is their discussion of their energy management all the way from procurement through to the middle kind of actual energy initiatives, all the way through to the end use. So it wasn't just focusing on specific energy use policies and efficiency measures. It kind of took a holistic approach. So I think that's our.
Thanks, everybody. That was really great, good slice of what else is going on around the country around this. For folks online, we were just having students present on topic of the day, just to kind of give a broader review of what's going on around the country. So without further ado, question. Is there anyone online where we can find who's presenting? All right. So.
Yeah. Can you folks online see the screen share? Yep. Okay, great. Hello, my name is Professor Michael Kane. I'm an assistant professor in civil and environmental engineering. And I work generally in the area of what is the future of civil engineering? What is the future of infrastructure as it becomes more and more automated? How do we make that automation kind of serve our needs and not just make things needlessly complicated? And so I'm going to talk a little bit about kind of homes, because that's a part of one of the major research projects that we're studying. And we're working on kind of translating what we're understanding about kind of homes and energy use and how people interact with energy use at the residential scale, and then hopefully kind of transitioning that also to include commercial spaces like Northeastern here. I thought that those two presentations were really interesting. I think that they kind of there are two different approaches there that I'm not sure we're seeing kind of nuanced in between what the two universities are doing. I kind of want to do a little poll of the audience here, a little thought exercise. So there were three kind of things that I saw that those universities were doing. They were doing some sort of energy efficiency. So they have equipment out there and they're trying to make it more efficient. So they use a higher efficiency boiler, a higher efficiency some sort of like heating unit. And then they might, so there's efficiency, there's conservation. So let's reduce the cooling set points, or let's make the thermostat more energy efficient. Let's set a set point that's more energy, uses less energy. Or let's make sure that the windows and doors are closed and not let air flow out the building, and make sure the shades are closed and the lights get turned off. So that's conservation. We want to be able to conserve energy. It's not that we're using it more efficiently, we're just not using it in certain areas. And then the last area that I saw that these universities were doing was transitioning their energy source to renewable energy, right? And all three of these, conservation, efficiency, and renewable energy, were all in the name of trying to get carbon emissions down to zero. If you had to pick one of those to get down to zero, if you are like, let's say you had to focus most of your effort into one of those, which one would you pick? Let's see conservation first. So is this the most important thing of like turning off lights and making sure our blinds are down? Any hands for conservation to get to net zero energy? Okay. How about energy efficiency? So the best equipment on campus, making sure that we can, so energy efficiency, some there. Okay. I guess we'll see how many. How about renewable energy? Is that the most important thing? Okay. So you guys, yeah, so you learned a lot in lecture one, I guess, or you knew a lot coming into this, that renewable energy is really the only way that we can get to net zero. We can't efficiency our way to zero. That would just mean not consuming zero, that would mean consuming zero energy, which isn't how our lives, our economy, how physics works. And so if we are going to transition to 100% renewable energy, we can try to save money and save some of that energy by doing energy efficiency and conservation. But what are the challenges that are holding us back from using 100% renewable energy? And that's where I think a lot of the things that we're going to talk about today are going to come in. So I guess a little bit about myself. I did my undergraduate degree and first master's in architectural engineering at Drexel University. It's kind of like Northeastern's sister down in Philadelphia, a strong co-op program. So I've been a big fan of co-ops essentially since I started school. Did my PhD and degree in electrical engineering at University of Michigan. And then I work for the US Department of Energy, ARPA-E. So it's their Advanced Research Project Agency, really thinking about what is the next generation of energy technologies and how do we make major leaps in energy technology and energy efficiency of the US economy. And I've been at Northeastern since 2017, running the Automation in the Built and Living Environment Lab, or the ABLE Lab. So if we're talking about renewable energy, it's all about when we talk about renewable energy, we talk about renewable electricity. There is some other energy, but they are secondary to a lot of the conversations. Most of the conversation kind of in the US has been moving more towards renewable electricity. Otherwise, we're talking about renewable fuels, which are coming from biofuels, or the B20 fuel oil, but even that was only 20% renewable oil. So if we're trying to understand electricity, let's understand the electric grid. So the way the electric grid is run now is assuming we control generation. So we have large, huge power plants that are 10 to 100,000. And we have, they're kind of all connected. So we can have nuclear, we can have renewable energy that we see here. And essentially this generation gets set up. Assume that we control that generation in order to serve our customers. And that power goes through the transmission lines. So it's like the highways of the power grid. They're really like the lines that you see kind of cutting through across America. And notice how that transmission system is well. Here, this tower, let's say that tower is a hurricane and or ice, and that tower falls down. The system itself be resilient enough at the transmission level that the power can kind of route around that. There's a lot of redundancy in the power system at the transmission level. But then we come down to the distribution level, where most things getting our power. Down here, notice how the line goes out here, unless like, so this is kind of showing a grid of the future where the kind of connect together. But in most areas in the US at least, this power line here, can you guys see that? Yeah. Would be there. So essentially the distribution system is set up like a tree. So if we have a power outage,
You want to take that?
oh, sorry. All right. Yeah. Oh. Yeah, there we go. Perfect Goldilocks zone. Okay. Okay, so yeah. So we have the our transmission system is highly resilient. Our distribution system is kind of like a tree. So if one branch falls out, all the leaves that are connected to that get disconnected. And notice how in this we see some power being produced at the kind of distribution level, but it's really not a whole lot in terms of how much power there still is being produced in centralized areas. So we have kind of huge centralized generation. We have transmission systems. So we might have very large factories, like a transmission customer that might be like an aluminum smelting plant that uses a lot of electricity. We might have customers that are like connected to very high voltages. I don't know, is Northeastern connected to the transmission? It's the distribution system. What's that? 13. Yeah, 13. So the Northeastern is connected to 13,000 volts. So kind of somewhere in this area, kind of in this gray area between these two lines. And then your home is connected at essentially 120 volts in a transformer that comes down to your home. And so some of these homes are able to have their load be controlled. And so if we can control our load, we can think about having less of this dispatchable generation, the power plants that we can control. We can put more fuel into a natural gas plant. We can put more coal into a coal power plant if we need more electricity. But we can't control when the sun shines or when the wind blows. So if we want to provide power, if we want to provide renewable power 24/7, we need energy storage and or the ability to control when we use electricity. So we have to transform the way we think about how the electric grid works from saying we control the power plant and we let customers do whatever they want to we can't control the power generation. We have to use expensive storage, batteries, some hydroelectric, but that's not usable everywhere. You can't just site hydroelectric everywhere. You need kind of elevation changes. And we need to be able to control when we use electricity so that we can use it when it's plentiful from the renewable energy. And that presents a lot of challenges because we never had to think about when we use electricity for. Unless you grew up or lived in kind of a developing country, in the United States, we always think if you turn the power on, we use the electricity is always going to be there. And from the residential perspective, it's always the same price, no matter what time of day, no matter when we use it. It's pretty much always the same price of electricity, barring changes over kind of year to year. Joe might get into, are you going to keep them charges? Okay. So it's a little bit different for commercial buildings, but so we have to think about how do we use these distributed energy resources to help balance this supply and demand on the electric. Both there's an economic supply and demand balance on the electric grid that needs to happen, but physics also says that if we put an electron into the electric grid, it has to be used essentially immediately. So we either need storage, which is expensive, or we need to be able to control these distributed energy resources. And instead of controlling thousands of power plants in an area, we have to control hundreds of thousands to millions of homes, control their electricity, control commercial buildings' electricity consumption, which becomes a lot more complicated. So let's look at how buildings are designed and how we think about how buildings operate. So essentially, we interviewed building operators all over the world. We've interviewed 70 building operators from 19 countries, I think. Half of them listed that they want to, this is commercial buildings, they want to make sure that the people inside of the buildings are comfortable. We build buildings to keep us outside, like to keep the elements, the outside and make the inside comfortable, right? That's why we have buildings. And so half of them listed that as their top priority. And a third of them listed energy as a priority amongst the top two of them. So they want to reduce energy consumption. So how do we do that? Well, way back in historic times, if you will, we just built walls. And we said, okay, well, log cabin walls will help protect us from the elements. And then we realized we could get better at kind of insulating and sealing it with new foams and new kind of technologies. And then we've gotten really good at essentially creating very well sealed, very insulated buildings that the heat can't come in or out of the building unless we control it. That's essentially the passive house standard. But we can't efficiency our way to zero. We have to put heat into our buildings during the winter, and we have to cool our buildings during the summer. There's some cases where that's not true, but in pretty much all cases it is. So let's look a little bit at the history of this. So fireplaces, but they were really inefficient. A lot of the heat goes straight up the chimney. In most modern houses, a fireplace will make your house colder even if there's a fire in it. Because in order for that fire combustion, right? Combustion requires heat, requires fuel, and it requires air. That air is coming from the inside of the house to feed the fuel, and then that air, that fumes, the exhaust goes up the chimney. Where do you think the air in the house comes from that ends up going from the chimney? So air is going up the chimney, air is leaving the house. The house doesn't just like suck into a vacuum, right? We don't lose all of the air in the house. What balances that? I think someone out there said. The air comes from the outside. It comes through all the cracks in the doors and the windows. And so you're pulling in all of this cold air when you're running a fire in your house. So you might be really warm in front of the fire, but everywhere else you're not. So we got better about kind of designing stoves. And then we thought, well, a stove is really only hot right by so can we distribute that heat around the house? And so that's where we get to boilers and furnaces that blow or pipe the air around the house. And commercial buildings are not too different. And then we got better at creating high efficiency boilers and high efficiency furnaces. In these systems, it's nice to be able to control them in some way. We can kind of think about, we think about the thermostat as being the base, but it's really, thermostat really just kind of goes back to, automates the part of feeding fuel into our system, feeding fuel into our heaters or controlling our air conditioners. Thermostat was only invented like 100 and some years ago. So thermostat is actually a relatively recent invention, even though we kind of think about it as so standard and simple. Then we get programmable thermostats, the programmable thermostats in the 80s and 90s and early 2000s. Less than 10% of people that owned a programmable thermostat in that 30-year period even programmed it. They owned a programmable thermostat and they just installed it and used it as the same chunk of metal that was in their walls that was from 150 years ago. With smart thermostats, it's getting a little bit better, but they're much more expensive, but they provide some other kind of consumer benefit. So it really kind of shows that it's really hard to sell energy efficiency, for example, just the programmable thermostat. The only thing it did was it changed your set point to a more energy conserving set point when you weren't home, and you had to program it. That was the only feature it did. It only promised to save you energy costs. It didn't promise to make you more comfortable. And it didn't promise to make it kind of help balance energy throughout the house. But here we have smart thermostats. Smart thermostats promise to be more convenient. They promise to not only save the energy like they used to, they promise to help make your house more comfortable by balancing the temperature throughout your house. And they do it in a way that, is kind of very, very convenient. And so most energy efficiency, at least at the consumer level, is sold not as energy efficiency. Think about the Tesla. You don't think about the Tesla being sold as an electric vehicle that's super green. You buy a Tesla because it's a really fast sports car. And they're working on kind of transitioning their way towards just a consumer car. But even then, they're not thinking about it as necessarily, they're not selling it as a green vehicle as the head of marketing. So we have to think about it. I think a lot of you in the audience are outside of engineering from business school. So I think the way that we sell or we think about transitioning our economy isn't just greenwashing everything. It's thinking about how we can make energy efficiency and renewable energy into higher value products. And then also think about how we design these into systems that can handle extreme temperatures, that can handle yearly energy efficiency kind of variations, and then adapting to changes, adapting to global warming. So things that we are designing now, are they going to be sufficient in 20, 30 years? So what does the future hold? So I think there was a reading assignment that was sent out that you may have read that on grid interactive efficient buildings, thinking about how buildings are interacting with the grid to make essentially things more efficient and to allow more renewables. Talking about how we think about the grid and people. So we have the grid here, we have the buildings, so they kind of interact through some sort of building automation system. The outside environment affects the building by hot outside, we have to cool it. Cold outside, we have to heat it. And then occupants play an important part of this here. So traditionally, we think about the electric grid as we control generation to match load. So I said that already. And let's say, so this is a graph of the load in California for a given day, April 22nd in 2014. So 20 gigawatts, that's a real unit of energy, 20 gigawatts of energy, plus or minus, vary between 20 and 30. But also in California that day, there was wind energy that was essentially wind is nice because it blows pretty constant all day. And solar, obviously, only when the sun was up. Now, the traditional way of thinking about the grid is that we control generation to match load, but we can't control that within solar. So what they do is they just say, what is the net load? What is the load, which we assume we can't control, minus the generation we can't control? And that gives us essentially what is the generation out of the things that we control that we have to produce. And we want to think about how do we drive this gray area, essentially fossil fuel powered generation, how do we drive that to zero? And so obviously we need to increase our wind and solar generation, but we can also think about reducing when we use our electricity. And so if you look at this net load, we have this big peak out here that is not when the sun was shining. So we have this peak in load that doesn't balance out with our renewable energy very well. So we have to think about taking this peak and using something like what's called demand response, changing the demand for electricity in order to help kind of cut down that peak. And so that we only have to produce a generation. So it's not just what is our average energy use over a year, it's how much energy do we have in kind of these peak times. So we can model building physics very well. There's a lot of software out there that engineers use that can help model kind of how the environment, how the equipment in a building is able to keep the inside comfortable. But the way people interact with the building is a lot more of a gray area. Human behavior is incredibly complex, as I'm sure all of you know, and thinking about how we incorporate that into our engineering models, our engineered systems, and how we think about kind of selling these systems from the business aspect or other aspects. So in my group, we're studying human physiology, so how our bodies kind of adapt to the environment. Then how do we think, how do we perceive, what is the cognition of our understanding of the environment, our physiology? And then we have our decisions and actions. So do people make rational decisions? And if they think they're making rational decisions, they might be, but they might be doing so with limited information. So it might look irrational to other people. So one kind of case study in this ability to kind of shed load here was in Worcester, Massachusetts, so not too far from here, working with the city and National Grid, their local electric utility. They tried to essentially they would just take thermostats. People would opt into this thing, and they would get paid maybe $100 a year to participate into this study. And the electric utility would control their thermostats, and about 10 times a year, primarily on the hottest days out of the year, when the electricity demand was the hottest because there's so many air conditioners out there running, they would just shut off the people's air conditioners for anywhere between 3 and 8 hours. And what we see is the longer these shut-offs are, in order to help shed these peaks or shift the energy use, the longer these shutoff periods are, the more people either opt out ahead of time or override. And we see over, essentially, if we add up this 25% plus this extra 5%, roughly about a third of the people are getting upset by this automated system that is controlling their thermostat, that's not providing their number one goal of being inside, which is to be comfortable. So we get a bunch of confused people not understanding why this automated system, why they have to fight with this automated system. So how are we tackling what does the future of this look like? One thing that we have is we're working very closely with a smart thermostat company, Ecobee, and we have data actually now up to 100,000 homes. We have data from the indoor temperature, the outdoor temperature, the set point. And we can learn a lot about these homes. I'm going to skip over this. This is just showing that as we change the temperature more, the more uncomfortable someone is, the quicker they're going to respond. So if you're very uncomfortable, you're like, I can't handle this, I'm going to go change it. But if you're only a little uncomfortable, it's going to take a little bit longer for you to kind of build up the frustration in order to get off your butt and go change your thermostat and go override this system. So thinking about these sort of psychological responses is pretty important. But we're only observing the behavior. Psychology is very kind of internal. Like there's a whole field of social science that does surveys and interviews and all these different things. But if we were to go out and do interviews, and I want to really understand your response to automated systems and changing environments, what did you have for breakfast yesterday? Okay. Can anyone, like, your ability to remember something even 2 days ago, about half the people when I ask that go, I have no idea. Unless you eat eggs every morning and that's just your habit. So people remember habits very well, but they don't remember kind of different changes throughout. So interviews aren't going to provide us this kind of really intimate understanding of how people react to a changing environment. So what we're doing is we're working essentially with kind of smart watches and providing just-in-time surveys. When something in their environment, how do we think about that? And how can we ask them questions and then combining this with a bunch of other kind of sensor data. So some of this is happening here on Northeastern's campus. We have kind of a augmented reality kind of apartment on campus that we do some studies in Richards Hall. We work with some psychologists and behavior and health experts kind of sharing this space, thinking about behavior for health and behavior for energy use. We're doing some field tests, 30 homes all across the US. I'm doing longitudinal 2-year-long field tests. And we're thinking about we're also doing laboratory experiments with the national lab in Colorado, really looking at understanding the hardware a lot better. So I want to leave you with kind of that big picture. What is the future of civil engineering? And if you're not an engineer, what is the future of infrastructure? What is the future of energy? Big things. So especially in terms of automation, what is automation good for? Automation is good for things that are very complicated and to us humans look like anarchy. Automation, AI can find patterns in what looks like anarchy to us. Automation is good for things that are dull, dirty, dangerous, and difficult. Especially those are all areas where robotics really specify. Automation is really for things that we need to respond faster than a human can respond. So what is the future of kind of using computation to respond very fast? This is like we have an earthquake and the high-speed trains in Japan stop in their tracks before the earthquake gets to them. The system is so fast that it can detect an earthquake 10 miles away, and before that wave travels through the Earth's crust, an electronic signal is sent to the train to stop it so that it's not going at 300 miles an hour when the earthquake hits it. How can we think about the future of that for our infrastructure? And then also automation is great for complex systems and helping balance out kind of between kind of trade-offs in large complex systems. So I'll leave it with that. I think we're going to go to the next presentation and then I have questions at the end. So
Over questions. Thank you very much.
Sorry if that was a little.
No, that's fine. Let me thank you, Michael. That was really great. Now I'll let Joe Lalley, I probably should share. All right, Joe, you want to introduce yourself?
Thank you. Okay, good stuff. I'm Joe Lalley. I work in facilities management at Northeast. I've been here since January 2019, but I've been in the facilities arena since 1984, and certainly been working hard to. All right. Improve energy efficiency and our environmental options. Our impact on the environment for many, many years. But I just want to start out by pointing out that we have a saying in the facilities business: buildings are the gift that keep on taking. Usually given by a donor, they just take. And whether it's dollars to maintain them or it's energy to work them, they keep on taking. And as you were talking, one of the things that struck me is I thought back to about a year and a half ago. Anybody remember what happened about a year and a half ago? COVID, right? So all of our building automation systems were set to minimize energy consumption. One of the ways to do that is minimize air changes in a building. Have filters that are just the right filtration level so you get the rocks and stones and boulders and twigs out of the air, and use less energy. And all of a sudden, what do people want? They want to know that the COVID particles and the droplets are filtered out before they breathe them back in. How many air changes do we have? Well, except in lab buildings, we can't turn over air constantly. Buildings aren't designed for that. And if you try to do that in the summertime, you end up having mold issues. If you try to do that in the wintertime, you freeze the coils and the fans. So there was a balance. So one of the things we did was we increased the filtration on the filters that are in the HVAC systems. Went to what's called a MERV 13, MERV 13. Gets down to about 80% for 0.3 micron particles. Typically, a COVID particle is going to be about 5 microns if it attaches itself to an aerosol droplet. But we were dealing with a whole new realm of how we manage our buildings. And we completed all that migration by the time we started classes last fall. So, more efficient filter, takes a lot more energy to push that air or suck that air through the filter. Surprisingly, mostly because I think a lot of people weren't here, our energy bill actually went down. We're expecting it to go up. But that's just an aside. But one of the things I want to just piggyback on a little bit about your presentation is we're in the middle of trying to reimagine our energy distribution system on campus. We have a heating plant, which you can see right out the back window. That has about 10 to 20 years of more life on it. We have a steam distribution system, leaky as hell. We figure we have about 20% energy losses. We are carbon, I think, neutral as of, is the right word to use. And as of January 2020, we did that by going out and buying enough RECs to offset our scope 2 emissions. So we report 0 to the EPA for scope 2 emissions. That's for energy that's produced off campus, but used on campus. And you can buy, we're buying Texas wind RECs. At the time, they were 76 cents a megawatt hour. Now they're $7.50 a megawatt hour. And then we bought enough RECs to convert or offset after that for our scope 1 emissions. That's the emissions we make from producing energy on campus. We do that at the plant so that we are carbon neutral. We're not net zero, but we're carbon neutral as of January 2020. And if you want to have an interesting topic, I would encourage you all to go out and investigate the wonderful world of carbon accounting. Because those scope 1 emissions that we're producing over here by burning the gas on campus, I can go down the street, it's not quite that easy, but Vicinity, which is a local steam producer, has district energy in Boston, and they have a pipe that used to feed campus, but I go right over to the Marino Center, plug into that pipe, turn off my plant, still use the same amount of energy, but now it's scope 2 emissions, and now I can claim carbon 0. because they're producing green steam. I won't get into how they're accounting for the carbon, but that's a wonderful exercise that you all may want to engage in because it's a fascinating subject. So much like your graph, I won't spend too much time on this, there are power sources out there. In this case, for our electricity or for our steam, if you want to do it. In New England, the New England ISO independent system operator transmits their electricity around 345 kilovolts. In other parts of the country, it's around 500. It goes into a local utility substation. And then we have the currently 13 transmission lines, 4 of them to come to campus. We have 4 independent electric districts on campus. They don't talk to each other. We have a dumb grid. And we can't shift loads across parts of the campus. We use about 520,000 MMBTUs of gas at the plant, primarily used for heating, but it is possible to make chill water by powering a chiller with steam rather than electricity. We have a few of those out of the way. We use about 307,000 MMBTUs or 90 million kilowatt hours a year of electricity. And we use that for cooling, including the chillers that cool this building. They're electrically powered for lighting and for running our HVAC systems and many other things on campus. So that's sort of our current configuration. And one of the things our team, we're contemplating what our future is going to be. And that is, people say, well, just go electric. That's the way to get the green. And it just isn't that easy. So first of all, how are you going to heat the campus? Well, we go out and buy heat pumps. Well, once you get down to around 30 degrees, and that does happen in Boston during the wintertime, their effectiveness begins to drop down. And typically, as you get to 0, a heat pump's just going to be a big resistance heater with not very much capacity. And so that's a real challenge. And so that means you need a backup heat source. And what are you going to power that heat source with? Is a challenge, and typically it's going to be a fossil fuel. Our buildings were designed many, many years ago. We have buildings that are 40, 50, 60 years old, and they have steam all the way to the coil in the HVAC system. And so as we think about moving to electric, we've got to figure out a way to modernize our buildings and use something different, perhaps hot water coils. But that's a significant investment in the hundreds of millions of dollars over the years. And the other thing that we found, if we were to look at an electric strategy, is we have to increase the peak campus demand by 400%. Now, we have those 4 feeders I talked about the campus. We would need 4 times that many to feed campus on the current configuration, or we could switch to a higher voltage from the substation. And we would need to site a substation, or we would need to convince the utility to site a substation in the neighborhood that could benefit Roxbury and the rest of the community. But I don't know if any of you tried to site a substation lately. It's not a very popular thing. So you have the that challenge. And lastly, you have the availability of power. The local grid constraints. Anybody familiar with the big Texas outage last winter in February? Anybody want to take a hazard as what the root cause of that was, in my opinion? It wasn't electricity. Electricity in Texas was from gas generation. Yes, they have lots of wind farms that did ice up, but the real root cause was gas generation. When you have a gas plant or pipe coming into the gas plant, there's a pressure drop going through the pressure regulator to the gas-fired turbines or recips that are there, reciprocating engines that are there. And Texas, it never gets cold there. Well, it did. And what happened was these PRBs iced up. And that's why the gas generation stopped. Unfortunately, we were lucky because we're under a fixed price contract. So we weren't paying $1,000, $2,000, $3,000 per megawatt hour. So I slept very well that night. But those are just some of the challenges because nobody ever thought what happened though. One of the challenges in the New England ISO is the fact that we get all of our gas piped in, and that gas is your capacity. So if there's a gas crisis in this region, you'll have an electric crisis right behind it. So those are some things to consider. We are looking at a CHP, a combined heat power plant. We have a relatively small heating load at this campus, particularly in the summer. And one of the challenges for mine is we can size the turbines, and they're right now a pretty close match, because when the turbines run, they make electricity. So you have what I call a rate arbitrage. You use the increased cost of gas is more than offset by your delivery charges for electricity and all the demand charges that are built into the rate. And we can probably spend a good 20 minutes talking about that in another class. But our challenge right now is we don't have a heat load in the summer to use that heat. So if we run the turbines in the summer when we need the electricity to cool the campus or whatever it might be, we'd be putting heat in the campus. Well, that doesn't feel very good, and it's not very good environmentally. So that's one of our challenges looking at the CHD. And of course, again, not many people want certain things in their backyard. So that's sort of a nutshell what I wanted to share. I'd be happy to take questions when the time is appropriate.
Thank you. Thank you very much. People have any questions, any thoughts that came out of this conversation that you want to ask either Michael or Joe right now? Well, let's stop sharing here. So I think right now we find to do some kind of a breakout room. You do them here as well as online, and discuss a little bit about what we learned, what we're talking about today. Thinking about what are some interesting things that you learned about here around grid electricity, and what do you think some of the things that are relevant for Northeastern going forward, thinking about how can we talk with your fellow students, people in the class, about people in the Northeastern community, about what would be is kind of information to know that could help going forward with how we're planning to change our electricity grid. So is that any other questions? I think that's a good, just kind of I think there's a lot of information that came on there. I think it'd be good for everyone to just kind of introduce yourselves to your neighbors. I can give a little more directions, and just questions you might have, things you learned about this, then we can kind of come back and we can go around and kind of just continue some of those conversations you had. So I think groups of 4, 3 to 5 people, see your neighbors right here, introduce yourselves, say hi, take about 10 minutes, and we can set up some breakout rooms. Maybe I can kind of do that right now. So by all means, turn around, say hi to your neighbors, introduce yourselves, your majors, and talk about what you've been experiencing.
Think about how Brown's sounds like they were proposing to repurpose those.
Yeah.
And also.
All right, just wanna kind of wrap it up a little bit. Thank you. Any thoughts or questions? I can go around and call the groups, but maybe anybody want any reflection on what you guys talked about or anything that came up that you found interesting in your discussion? All right, you guys are right in front of me, so you're gonna start with you guys. What did you guys talk about?
Our previous experiences related with the topic we discovered there. He actually is my peer, so that was fun.
Oh,
And what he wrote about in his reflection also kind of tied into what we discussed today with his experience as a co-op.
So I guess we just mostly talked about various energy transition at schools, like specific programs that what comes to completely useful. Just kind of specifically referencing UMass microgrids.
all right, thank you. We're talking about the transition other universities doing around and for electricity and carbon, and he's talking about what's going on with UMass. How about you guys in the back? Anything you want to talk about, or would you guys discuss? Questions came up. Anything you had? Yep.
Step-by-step thing, time or they will talk about where it's ready for everything to be electrified, and then talk about physical access, where it's like some cold water, where we can talk to that and bring it down, so like that, and then we talk about this beauty, how to help.
Well, so you covered everything. That's great. Sorry for folks online, or we're just any questions online, by the way, just for anybody. How about you guys? Anything, any ideas, questions came up to this topic?
So we talked about how the human physiology and psychology plays a role in,
Yeah.
usage of electricity, and how in future automation could be useful in generating and also distributing things.
Were you surprised by it, or is just something that you've been thinking about previously? Or
This was it was surprising, but it was interesting to know that how it played a role in it.
Yeah.
And how humans are not thinking about how we can control the distribution of electricity right at the source to the houses.
yeah, all the choices that we make, all little choices that it really it adds up. Actually, a big question for you about with relating to the Texas incident, or just in general, like when one thing I've always is when those kinds of these rare events happen where the grid is super stressed. Do people? How do people react? I mean, in terms of like the point where it's about to like kind of go down. Like, are they just thinking I got to get as much energy as I can before it goes down? Like, how are like right up until that part? Like, what's the kind of interaction people have with the kind of these emergency situations?
I think it's the culture that we have is electricity is always going to be there. So I don't have to think about it. And then when it's not, all of a sudden you're like, oh shoot, can I drive to Home Depot to get a generator? It was interesting that a transformer on a telephone pole right across the street from my house, or on a power pole, started leaking transmission fluid, which you can imagine is probably not good for the transformer. And I saw it and called 911, and they called the fire department, and then they called the electric company. 3 hours later, the electric company was there. But the transformer was still working. It was just going to fail imminently. And it was a hot day, and I knew that a lot of my neighbors are like elderly, and we all have window air conditioners. And so I said, why don't you turn your air conditioner up, because I think that they're going to have to turn the power off in order to swap out this transformer. And they didn't really understand why I was asking them to, on a hot day, knowing you're going to lose power, turn your air conditioner to be really cold so that it takes a little bit longer for your house to get hotter throughout the day. And then maybe by nighttime comes and power is still off, we can open our windows because the sun is down. But just trying to communicate something that, like, it sounds simple at first, but it's actually pretty complex for someone that's like never had to think about when they used power before. And that's essentially the mantra that we've been using in our research is we can't change behavior. Changing behavior is immensely difficult, and oftentimes the utility companies are often seen as pseudo-governmental organizations, and they're trying to change behavior, that we have like very big brother kind of unsettling kind of feelings about it. So can we change the system to adapt to the users instead of making the users adapt to the system? So we saw that a little bit in Texas. So there were power plants that were going down because the natural gas to the power plants was getting stuck in these frozen pressure reduction valves. And so the grid was losing generation. Remember I said every electron that's generated has to be used immediately. We can't use an electron that's not generated. So there's less generation, which means that there has to be less load, but we can't control load. So what does the utility do? They just shut off entire feeders. That's how crude of a tool they have in order to be able to control load right now. And so they were essentially having to decide, does your neighborhood or does your neighborhood lose power? I need to shed 100 homes worth of power. Whose do I shed? And I guess sometimes it would just be like I hope that it's not, but I can imagine that it's possibly a flipable point about which feeders do they turn off. Not really accounting for maybe people who are on ventilator or have medical necessities or things like that, or their homes pipes freeze. So other parts of the Texas grid were using these smart thermostats, and what would normally be used during the summertime to shed load for extreme air conditioning use, they were using to shed electric load during the winter, but because of a variety of reasons, just wasn't enough.
Yeah, it was massive
and so,
failure.
but even then, there was a backlash. We follow kind of the message boards and the internet around these ideas, and people were saying, I didn't know that I signed up for this program. I bought this smart thermostat, they gave it to me for free, and now all of a sudden they're turning off my heat during this extreme winter event. So there's, on that side, there's essentially communication to be able to have people understand what the automation is doing and why it's doing it.
Thank you. Yeah, the human behavior, I mean, the idea of just going and, I mean, it's a little different now with COVID and everything, but in the office or in the school, it's like everybody dressed for a warmer office, you're turning the air conditioning down. So instead of 72, it's at 76, and everyone kind of wearing t-shirts, so everyone putting on a sweater and all that stuff. And those kinds of behavior communications, it's like, it's hard to get that across. All right, who have an what groups? You guys in the back, what were you guys talking about? Sorry.
Mostly about like greenwashing, how in my co-op I get a little bit where.
What co-op is that?
So I was doing marketing at home for dishwasher tabs.
Sure.
And there's this huge effort, more green and like develop packaging, change formulas, but on the back end, I found that a lot of it is like, okay, well, we can do this, but like, if it's this and this much money, people won't would have changed, so this is this much, it'll still look good enough, and will still stay this.
Yep.
That was a little bit, really happening.
I mean, the same thing happens on the energy side as well, in all aspects of this.
On that point, I have a question for, like, on a, let's say that you're considering 3 or 4 different kind of new projects that could pay themselves back in terms of reduced energy costs. What is it, an acceptable payback period? It has to be payback 1 year, 5 years?
Well, actually, we've been considering what are called energy conservation measures by energy services companies here. And that's always a struggle because they will sell you a bill of goods. One of the first criteria is, will the energy savings measure pay for itself within the service life of the unit? People will try to, yes, it'll pay for itself in 12 years, never mind it wears out in 7. But probably the best deal going over the years has been relamping. And so first it was more efficient. You went away from incandescent, so there was a big payback there, and we got tons of grants when I was working in New York State for my service. And then we replaced the fluorescents with more fluorescents, more efficient fluorescents. Got all kinds of money to do that, payback in 1.5 to 2 years. And now LEDs, we stripped that one off from our ESCO because the rebates from Eversource was so attractive. And we've done, I think, about 98% of all the campuses in Massachusetts. We've got a couple buildings we couldn't get into. Payback's about 18 months. So I like to see a payback within 5 years, 5% investment rate of return of standard we use at this university and many other universities.
Yeah.
But, something that has that kind of payback, always worth doing. But again, we try to find out where the megawatts are. We quit using the energy in the first place. That's savings of all.
Yeah, just to follow up on your light saving us around 3 million kilowatt hours a year ish.
307,000 MBTUs, about 92 million kilowatt hours per year.
No, sorry, the lighting program, LED lighting program.
Oh, that was about all in about $4.2 million.
Yeah, and we're saving about 3 million kilowatt hours a year. So which is almost 3% of our electricity load. This one lighting retrofit where we're putting in all LEDs and sensors for occupancy and light is a huge, amazing investment that we're having. So you might notice some of the buildings that now you walk in, the lights will be off, will come on when you're walking in, all the sensors and everything. So
there's just a couple other things though, if you think about looking at buildings, just going on the comfort thing that Professor Kane raised. We have, I don't know, can't remember the number, we have several hundred acres of roofs on this campus. And tremendous energy loss through, and also you don't want the water coming in. So part of our effort around planning the capital maintenance program is to keep the water out where it doesn't need to come in and keep the water in terms of pipes where it belongs. So we're being fairly aggressive about our building envelope program to keep the air, the tempered air in and the untempered air out, the colder heating, and also not losing heat. And the same reason you wear a cap in the winter, keep your head warm, is why you need to have a well-insulated roof on the building.
So is that the work on Snell Library? Is that?
The work on Snell Library started out with the roof project, and we sealed up the roof, and so the roof quit leaking into the building and started going off into places coming in the side of the building. So we have a big resealing program project going on right now that I hope is about to tighten that building up. Same thing with Egan. So it's just a combination of things. We also have about $42 million worth of window replacements that we're proposing to tighten up.
So are you seeing those benefits in moisture, but also in air infiltration and reduced energy costs?
I have not gone back and seen the energy cost yet because we're not done with the project, but I think the comfort levels are up. And the complaints for heating and cooling seem to be drifting down a little.
Thank you. Any last questions or thoughts, folks, for these guys? All right, there's nothing else. For the registered students, any questions on some of the communications we had and people know who's going to present for next week? Those all been, if you're not sure, well, now let us know and ask us. But we'll send you an email as well for mine. Yes.
Is there a class on Fridays?
Oh, correct. Thank you. So that class for Friday was a placeholder for the tour. We had to put something in there to get it going. Thanks for your question. So ignore that. Ignore that. The tours that we've asked you to sign up for, those are in those places. We didn't know we didn't have the tour time, so we just put a placeholder. So the Friday the 24th class, there's nothing going on there. The tours are taking up those times. Thank you for asking that question.
Do we have to go to one or two?
Two. If you have a problem making two, we can talk about it later, but we have some room for two of the tours. There's an extra room, so if there's only room is the ones on the 6th and 28th. You're more than welcome to go on those two. Let us know.
So generally, for people who filled out that survey, just go to your first impression portal. It's kind of worked out. So some of them will be a little full. But you're welcome to go to